Okay, so this video is going to go over another conjugate beam example so that you have more than one to go off of for your final. And this particular example is a little bit tricky, so I want you guys to pay close attention to it. And I'm going to kind of explain it before we kind of jump into solving it. So the idea with conjugate beam analysis is, if you remember from the previous example, you have to turn the moment diagram essentially into the load on the beam. That's all you have to do. Draw the moment diagram and then make the moment diagram your load. But you can imagine what happens when you have like a super complicated moment diagram. It starts looking crazy on your beam and you can't even analyze it because it's not from those basic static concepts that we know. So you always want to make sure that you're not doing anything more than a triangular distributed load, a constant distributed load, point loads, and things like that on your beam. Because then it's just not realistic, and then conjugate beam method wouldn't necessarily be the best method to use. So I'm going to show you now what we can do to make sure that our loading is still simple enough to kind of solve and put together. So what we want to do for this example here is we're going to separately analyze the 8 kip load, the 30 kip load, and the roller support at C, okay? And that way we'll be able to kind of make this loading on our beam look a little bit better, okay? So the first thing here, let's draw our shear and moment diagrams for this member. Okay, and what I'm going to do, I'm actually going to draw the shear and moment diagrams split up for each of those loads here. So let me get to that here. I'm going to come, where should I put this? Okay, actually, let me go like this. Okay, we'll say that this here is equal to just my beam with the 8 kip load, okay, plus my beam with the 30 kip foot moment. And of course, let's not forget this little hinge here. We have a little hinge. Plus my beam with some reaction here, CY. Okay. And this makes this a determinate structure that I can solve instead of one that has 4 unknowns that I'd have to kind of pull that hinge apart to solve for. Okay. So the first thing I want to do is I want to solve for the unknown reactions at all of these points for this, and this for each system here. Okay. And what I'm going to do actually first is I'm going to come here, and if I were to analyze this system, I need to figure out what this CY is so that I can put it here as a reaction force. So in order to figure out what CY is, I'm going to have to pull this member apart first. So I'm going to say that I have this beam here attached to this beam here. Here I have a CY. Here I have an AX, an AY, an MA. And then here I've exposed equal and opposite BX. And I'll say here, actually, let me draw this a little bit better. Oops. We'll call these BY and BX. Okay. And I'm going to put back my original loading for now. Okay, and I'm going to analyze both of these sides in order to get my reaction. So I'm going to say sum of moment at point B has to be 0. Counterclockwise is positive, so I have a cy times 15 minus 30, and I get cy equals 2 kips, which is what I needed for this. Okay, so here I'm going to replace this cy with 2 kips. Okay, and I'm going to solve now for the moment values or the moment diagrams for each of these loads. So I'm going to come here and I'm going to call this 1, 2, and 3. So let's start here with 1. Okay. Now here we just have a cantilever beam, and what we have is we have some AX. We assumed here we'll say AY, and we have some MA. We can already see that AX is equal to 0. If we sum forces in the Y direction, we can see that AY equals 8 kips. And let's say we sum moments about point A, set them equal to 0, counterclockwise is positive. The 8 kips acts 12 feet away. We end up getting negative 8 times 12 minus we get MA is equal to 96 kip feet, but in the opposite direction, so counterclockwise. And this is for case 1. Okay, now let's do the same thing for case 2. Okay, here we have case 2. Actually, we should draw let's draw the shear moment diagrams for this before we do that. Okay, it's probably a better. So here, for this beam, we have 8 kips, and we have so we have a shear diagram. Basically looks like that. And we have a moment diagram, which this is the important part. We'll put it all together later. Our moment diagram, which basically comes here. We have negative 96 up until this point. And this is M, and I'll put M1. This is very important here. Okay, now let's do this for case 2. Let me copy case 2. Okay, and again, now we can solve for, let's do the same directions here. AY, AX, MA, and this is just for the 30 kip now. So we're going to see that here we actually have an AX value, which is 0 from sum of forces. We're going to sum moments around point A, set them equal to 0, counterclockwise is positive, and we get, basically we can see MA is equal to negative 30 kip feet. So again, it's going to be the 30 in the basic, I'm going to take out the negative here and just write 30 counterclockwise. And this is for case 2. Okay. Okay, so we have no shear for this part. And we do have a moment diagram that's constant. It's going to be M2 at this 30, goes down 30, and then just goes up by 30. Okay, so we have 1, 2, and then now we need the third, which is for this cy of 2. Let me copy this here. Once again, we have our AX, AY, MA. We're going to say that AY now is equal to -2 kips. It should be going in the opposite direction. AX equals 0. Sum of MA equals 0. Counterclockwise is positive. -MA plus 2 times, what was the length? 15 plus 24 equals 0, and if we solve all of this, we get MA equals 78 kip feet. Okay, and we put it in the right direction already. And so last thing we're going to do here is again draw that shear diagram. We see here we go up to 2, nothing, down, and then here our moment diagram should be should be linear. We're starting at 78. We're going to end at 0. And now we have, this is M3. And I forgot actually the over EI, of course. Okay. Now we're going to combine all of these three. Combine all moment diagrams as loading. And this is our conjugate beam. So here is our beam. Let's add all of our loading on there. So the first load we have the, what was it, -96. So I'm going to draw that probably this direction. The second one is the -30. I'm going to put it up here. It doesn't matter if you put it above or below as long as you draw it going down. So they have, the arrows are what matters. And this is going to be the -30 over EI. And the last load we have on here is the +78. And so we have something like this. And this now is our conjugate beam. And so that we know all of the dimensions here, we have from here to here 12 feet. Then we have another, let's say 12 feet. Sorry, these dimensions are obviously off. They're actually really off because this is supposed to be 15 feet. But you get what's happening. Okay, now that this has happened, we finally have everything we need to determine our slope and deflection here. So let's go back and see what we're looking for this problem again. We want the displacement of the pin at B and the slope of each beam segment connected to the pin. So we want delta B, and we want theta B from the left and theta B from the right. That did not look like an R. Right, there we go. Okay, so let's come here. And the first thing we're going to do now is we need to basically sum forces just to the right of that point B, which is, let's see where point B was on this beam, at 24 feet. So this here is our point B. So what we're going to do is I'm going to put all this in green. Okay, so if I do that, I need to get all the resultants of these loads. So here's the triangular load. Here is the 30. And basically what I have here, I have 225 over EI. I'll have this 3.6 over EI. And I'll have, 450. And here I've exposed a VB prime to the right and an MB prime. And now I can sum these forces, and I can say VB prime R plus 225 over EI minus 450 over EI minus 3.6 over EI equals 0. And now I can solve for this theta value. And I can get theta is equal to, okay. Now what we want to do is we want to figure out this is the rotation. So we need to figure out now the displacements for each side. So let's continue with the other side. And get all of our resultants for this side. This is the resultant of the 30 down here. And then on this side, we're going to have the VBL from the left side and the MB from the right side. Now we can sum our moments here. And then basically the internal moments now at B prime have to be the displacement of the pin. So because that's what we know about the conjugate beam, that was part of our theorem. So we can say now if we plug in EI, displacement at that point is negative 4.58 inches. And then if we sum forces just to the left of B, we get this VB prime L plus the resultant so we're just adding all those resultants and we can get theta B to the left equals VB prime to the left equals 0. Okay, and basically this delta B is equal to the MB prime. These are what we're looking for here. Okay, so basically that's all you need to know from this huge 80 slide PowerPoint. We're not going to worry about the other stuff. We're just going to keep it at conjugate beam method. And during our final review, I will answer questions about this and go over it in more detail if you guys need more help.